Exercise 5. This one has two parts. In part A, we are given this matrix. We have to first of all show that it's a nilpotent matrix. So some positive integral power of it will be the zero matrix, 3 by 3 zero matrix. And then we have to find its invariants and Jordan form. And in the second part, we have this other matrix. We have to prove that this is not similar to this. So let us start by showing that this is nilpotent. So to show that it's nilpotent, you of course have to find the higher and higher powers of this matrix until you get the zero matrix. Oh, and one more thing. Before we do anything else, let us give these matrices some names so that we can use them easily. Let's call this A and this one B. Let us also see what the entries are. The first row consists of ones, the second row is constantly -1 and the third row is 1, 1, 0. B is almost like A, but the only change is that here we have 0, whereas in A here we have 1. Okay, yeah, I can start from here itself. So we have to now do some matrix multiplications. A itself of course is not 0. So let's calculate A square. Alright, so what shall we get? Let's do our usual stuff. First row times first column. 1 minus 1, so they just vanish, plus 1, that means 1. First row second column. 1 minus 1 plus 1, again 1. First row third column, 1 minus 1 they vanish, plus 0, so that means this is 0. Then minus 1 minus 1 give us plus 1, so minus 1 and plus 1 vanish, and minus 1 times 1 is minus 1, then minus 1 plus 1 minus 1, same. Finally minus 1 plus 1 plus 0. Then the third one, 1 minus 1 0, 0, 1 minus 1 0, 1 minus 1 0. Okay, so this is A square. A square is not 0. Okay, let's calculate A cube. A cube is A times A square, or A square times A, in any manner you can calculate. Let me first write A. A times A square. This is A square, so 1, 1, 0, minus 1, 0, 0, 0, 0. One minus 1 0, 0, 1 minus 1 0, and this column is entirely 0, so first row times third column is also 0. minus 1 plus 1 0, minus 1 plus 1 0, and this one of course is also 0. Finally 1 minus 1 0, 1 minus 1 0, and this one is 0. So yes, finally we are getting the 0 matrix. Hence A is nilpotent. Okay, so that's pretty easy and straightforward. But now we have to next find the invariants of A and the Jordan form. For that we recall that one example that we already have seen in the text in the section where we proved that fundamental theorem, the form in which we can get any nilpotent matrix, that thing. So there, if you remember, we started by considering the standard basis vectors of F3, the vector space F3. Consider, let me continue from here itself. Consider the standard basis vectors for F3, which are these: 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now what we do, we see the effect of the linear transformation A, that means our matrix A, on these basis vectors. But how is the matrix A linear transformation? See, we can actually, the matrix itself, we are not saying that it is itself a linear transformation, but it can be used to give us a linear transformation whose matrix will be it. Okay. And that transformation is just this. That transformation also, say, we are calling A. Actually, I should put this within brackets. And how does it act on the vectors of F3? Say we have a vector V in F3. It acts on V like this. What does this VA mean? You can see this. See, V has 3 coordinates or components, right? V looks something like this. Now you can consider it as a row matrix also. That means which has only 1 row and 3 columns. So it looks like this. If you multiply this and A in this order, A of course is also a matrix, and this product makes sense. Why? Because the number of columns of this row matrix, which is 3, matches with the number of rows of A, which is also 3. And what will the product look like? The product will also be a row matrix. That's because this is a 1 by 3 matrix and A is a 3 by 3 matrix. So the product will again be a 1 by 3 matrix. And that corresponds to a vector in F3 again. The entries of this product matrix, which will also be a row matrix, will be the components or coordinates of that vector. And this is a linear transformation. We are talking about that linear transformation. So now if we apply that A in this manner to these vectors, what are we going to get? Let's see. Actually from theory means you go to that result which tells you that any linear transformation T which is nilpotent has a matrix of this form. That thing. You go to the proof of that, MNR. In that, we work with these vectors and we applied T repeatedly on them, and that gave us a basis. From that basis, we are able to then say other things. From that basis itself, we will get Mn1, Mn2, these things. And if you remember, these are the invariants of T. Okay? And in the scheme in which we have the proof of this fact, in that scheme, the new basis, whose vectors we called V1, V2, V3 and so on, V1 is just U1. I cannot simply just write like this. Now, V1 is just U1. What is V2? V2 is V1A or U1A, same thing. Now, what will you get if you calculate the product this times A? Let me show it here itself. I don't want to write it fully. 1, 0, 0. And what is our A? This is A. So what will this product be? 1, 0, 0. 1, 0, 0. And then again 1, 0, 0. So that means the vector that we are getting is 1, 1, 1. If you write that 1, 1, 1 in terms of U1, U2 and U3, you get U1 plus U2 plus U3. Okay, so this is our V2. And then another one, V3, this is V2A. Because we now already have V2, so let's calculate V2A here itself. Just have to change this. Now what shall we get? One minus 1, so they vanish, plus 1, 1, okay. 1 minus 1 plus 1, 1. So that's also like before, but then 1 minus 1 plus 0. So this one will be 0. That means this vector is 1, 1, 0. 1, 1, 0 in terms of U1, U2 and U3 is U1 plus U2. U1 plus U2. And from theory, we now know that just like U1, U2 and U3 form a basis for F3, which we call standard basis vectors, V1, V2, V3 also form another basis. And what will be the matrix of A it sounds very peculiar because A itself is a matrix, but here A is being interpreted as a linear operator. The matrix of that operator in the new basis V1, V2, V3 will be, now we can write that because we have this. Well, I think I should perhaps also show the effect of our linear transformation A on this V1, V2 and V3. Although we already know about that from theory, from that theorem proof, all these things, but still let us just see. Note that it is nothing difficult at all. It comes directly from how we have these vectors V1, V2 and V3. Note that V1A is just V2 because that's what it is. What is V2A? V2A is V3. And what is V3A? V3A is, if you express it in terms of V1, V3A is V2A square, but V2 itself is V1A. So this is V1A cube. However, A cube is the zero matrix. And so as a linear operator, it's also going to be the zero operator. So this gives you 0. You do understand what this 0 is. This 0 is the 0 vector in F3. So now we see what A does to each of the basis elements V1, V2, V3. So now we can write the matrix. Hence, the matrix of A in the basis. Actually, this itself is the basis that we were seeking in that theorem, in which if you express your linear transformation as a matrix, then you have that form Mn1, Mn2, that thing. In the basis V1, V2, V3 is. So how will you write the matrix? Let us first see what A did to V1. V1A is V2. In terms of V1, V2 and V3, what type of linear combination is V2? 0 V1 plus 1 V2 plus 0 V3. That means the first row of our matrix will be 0, 1, 0. What about this one? This will give us the second row. What type of linear combination is this one? In terms of V1, V2, V3, 0 V1 plus 0 V2 plus 1 V3. And this of course is 0, so all the scalars are 0. Also at this point I should mention one more thing. You may remember that we are consistently writing linear operators on the right side and the vector on which they are being applied on the left side. This is not conventional. The usual convention is of course to write a function first, then followed by its argument. In this book, however, we write like this, and the same thing is followed for linear operators as well. So, we write the image of the vector V under the linear operator T as Vt instead of T of V. Now, the notational convention has an effect when you write the matrix. If you are following this convention, okay, so what do you normally do to write the matrix of a linear operator in some basis? You apply the operator on each basis vector and then you express each result as a linear combination of those basis vectors again. And then you note which scalars have appeared in those linear combinations. When you follow this notation, the scalars that appear in the first linear combination give you the first row. Okay, so for example, here we have 0 V1 plus 1 V2 plus 0 V3. So 0, 1 and 0 give us the first row. However, had we followed this notation, those scalars would have become the first column. Why this disparity? This is because in order to keep the multiplication rule for linear operators intact, matrix multiplication. I mean, in the universe of matrices, when you multiply two matrices, it's the same as composing two linear operators, whose matrices they are. In order to maintain this thing, we have to follow the different rules for writing the matrix of a linear operator depending on how you are writing the operator. For us, since the operator appears after the vector, it appears to the right side of the vector, so the scalars become row, not columns. Since this is not the usual way of writing things, that is why when you normally follow this notation, there the scalars become columns. Alright, so now this is our matrix. Does it have that form that we saw in that result, Mn1, Mn? Yes, this itself is, when we have that matrix as a block diagonal matrix, as a block diagonal matrix, this itself is one block. This itself is one M, because you just see its form. The matrix has almost all entries 0 except the super diagonal, the diagonal above the main diagonal where it is 1. So that's it. This is the Jordan form. And because we have got only one block, that is why the invariant, there is only one invariant, which is 3. This is the Jordan form of A, which has the only invariant three. Now, how does one get from A to this? We are saying that this is the Jordan form of A, which means that it belongs to the same similarity, this one belongs to the same similarity class of A. So, some invertible matrix is going to give us that similarity. What is that matrix? That matrix can be obtained as the change of basis matrix from the basis U1, U2, U3 to V1, V2, V3. That also we can write. Although there is no need, but still, in fact, if, let me call that matrix C, if C is the change of basis matrix there is no need to write anything more from the basis U1, U2, U3 to V1, V2, V3, it's understood. i.e. C is, so what type of change did we see here? uh, first there was no change. V1 is simply U1. So 1 0 0. What is V2? V2 is U1 plus U2 plus U3. 1 1 1. And then V3 is U1 plus U2. 1 1 0. Then one can verify it can be verified that C, let me write it here, CAC inverse is this matrix. Because you now have C and you of course already know A. So what I want you to do is I want you to really do this calculation. You calculate the product CA, you then also find the inverse of C in your usual manner, whatever method you want to use to find the inverse, and then calculate the product of CA and C inverse. You will see that you really get this matrix. Okay, so that's part A. Now next we go to part B. In part B we have to show that the matrix there is not similar to the matrix in part A, that means capital A. We will do so by showing that the matrix in part B, which is capital B, we have called it B, is not nilpotent. So let's see what the powers of B are. B itself is also, it itself is not a zero matrix. If you remember, it is 1 1 1 minus 1 minus 1 minus 1 1 0 0. That is not the zero matrix, 3 by 3 zero matrix. Let's see what B square gives us. We have, and in fact we don't want any power to be 0. But how can we figure that out? How can we make sure that no power is 0? Do we have to calculate all powers? That is impossible. Then what can we do? Let's see. One, one, one. Minus 1, minus 1, minus 1. 1, 0, 0. But let me just see also. Is it? Yeah. I don't want to make any mistake here. Again our usual pattern, 1 minus 1 1, so that means 1. 1 minus 1 0. 1 minus 1 0. Minus 1 plus 1 minus 1. Minus 1 plus 1 0. Minus 1 plus 1 0. 1 0 0. Okay. 1 0 0. So this is going to be just 1. Like this. Alright, fine. But what about B cube? B square hasn't been a zero matrix. We want that. Okay, so it's okay. So I have written B square first and then I will write B. So that will give me B cube. Alright, so let's now carefully calculate this product. 1, 0, 0, 1. You can clearly see that in multiplying these columns by the first row, actually the entry that matters is the first one. The others are 0, so that do not have any effect. And 1 is of course going to get multiplied with the first element of each column. So that's why the first row is simply 1, 1, 1. Next, minus 1, 0. So similarly, this one is going to be minus 1, minus 1, minus 1. Because minus 1 gets multiplied with the first element of each column. The others are going to get multiplied with 0, so they are not going to have any effect. Next, 1, minus 1, 1. 1, minus 1, 0, 0. 1, minus 1, 0. So you see that very nicely, B itself has come back. It is just the matrix B itself. So now can you conclude that no higher power will be 0? You can actually, in spite of not calculating any higher power. Why? Because if you now calculate, say you want to calculate B to the power 4, that is B times B cube, but that because of this identity becomes B times B, that means B squared. So you get back B square is non-zero. Then you calculate B to the power 5, which will be B cube times B square. So B cube is B, and then B times B square, again you get B cube, so again you get back B. So you just keep cycling with these powers only. You do not have any chance of getting 0, no matter how large a power of B you consider. That is why we write from these, it's clear that this is not equal to 0 for all positive integers n. Positive integers in this text are natural numbers for us. That's why we write this. N comes from the set of natural numbers. If this part does not really look very satisfactory to you, I ask you to come up with a small argument where you use these calculations and show rigorously that this cannot be true. Say by assuming that B to the power n is actually equal to 0 for some positive integer n, then arriving at some kind of contradiction. But I don't think I need to do that. It's pretty clear why this can be concluded. Thus, B is not nilpotent. Hence, B is not similar to A. If you take a nilpotent matrix and you take a conjugate of that matrix, then the conjugate will also be nilpotent. You can see how. Say suppose you have a square matrix X, say X is nilpotent, and you take an invertible matrix Y of the same dimension as X, of the same size as X, and consider this conjugate of X by Y, and suppose that the nth power, where n is a positive integer, of X is 0. Then what is the nth power of this? If you write n copies of yxy inverse one after another, you will see that there are some cancellations, some things happen, and you end up getting this. This is in fact also a form that you are well familiar with from group theory. In group theory, we see this type of thing. But this is 0. So, this is also 0. And that is why if X is nilpotent, then any matrix conjugate to X, or in the language of matrices similar to X, is also nilpotent. And that's why B cannot be similar to A, because B is not nilpotent but A is nilpotent. So that's the solution. And let me end this video here itself. There are many more exercises and we will solve each one of them hopefully, but it will take some time. And tomorrow also we have our usual analysis upload. We have already started the section on Riemann-Stieltjes integrals. We have simply just seen the notion of alpha length. So after that we will see how we can build this theory parallel to what we did in Riemann integration. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.